before going to the first topic, what I would like to uh, do is spend some time on the assumptions that we do in this course, so that it will be retained for the entire course. So there are some simplifying assumptions that are made as far as the devices are concerned. So we do analyze a lot of power electronic circuits using these simplifying assumptions. You may be familiar with some of these. Okay. So for the sake of uh, stating all these assumptions in the beginning, so that I will not be repeating these assumptions every time. Okay. So when we do the analysis, these assumptions are implied. So first of all, there are uh, uh, three categories of power semiconductor devices. So if you look at power semiconductor devices, there are three categories. One is diode. So all of you are familiar with the symbol of a diode. So I have two terminals, A for anode and K for cathode. Now we all know that if the potential of anode is higher than that of the cathode by a certain value, it is forward biased and it starts conducting. Now the assumption that we make here is, if the potential of the anode is just higher than cathode, so that even if it is any value, the potential difference between anode and cathode is any value greater than 0, okay, then we say that it's forward biased and it starts conducting. Okay. There are only two terminals, A and K. Both these are power terminals, and there is no way to control the uh, state of the device. So there are two states, on state and off state. So if I want to go from one state to other, it only depends on this power circuit in which it is connected. So depending on whether it is forward biased or reverse biased, either it conducts or it does not conduct. So we say that a diode is an uncontrolled device. The next category of power semiconductor devices is thyristor. The symbol is similar to that of diode, except for a minor addition, and there is an addition of a terminal as well. So I have the anode and cathode terminals which are there in the diode also, and there is an additional terminal, gate terminal. G is the gate terminal. So anode and cathode are power terminals, whereas G is the control terminal. So in the case of thyristor, if it is forward biased, now the definition of forward biased is similar to that of diode. If the potential of anode is greater than the potential of cathode, then if a gate current pulse is given, that means if a positive current flows from gate to cathode, or if just a pulse of positive current flows from gate to cathode, then it starts conducting. So we say that it's in the on state. Now if it has to go to the off state, that means if it has to stop conducting, then somehow the power circuit should be in such a situation, should be in such a condition that the current itself should go to 0. Now there is no way of providing a pulse as we did in the case of turn on using the gate terminal. So if I want to turn on, so I can do the turn on as long as the thyristor is forward biased. I can turn it on by giving a signal using gate terminal. So I give just a current pulse that flows from gate to cathode, a positive current pulse, and that will actually turn on. But turning off is not possible by control. Turning off is only dependent on the power circuit. So if the current goes to 0, and not only that's not the only condition required for turning off, current should go to 0, and then it should remain reverse bias for a certain minimum duration. Only then it will turn off. Okay. So there are a few things that are neglected. Now both in the case of diode or thyristor, when the device is on, the voltage across the device is actually 0. So we neglect the voltage across the device. So that's what we mean by ideal device. So we'll assume that these are ideal devices. Now this is actually justified because we are talking about voltages of the order of kilovolts, or I mean, if you add up, it is hundreds of kilovolts. So a small fraction of a volt is actually negligible. So of course, it's not just a fraction of a volt, because many such devices are connected in series. So they will add up to actually make it a significant amount of voltage, but still negligible compared to the overall voltage. Okay, so that's why we say that whenever the diode or thyristor is on, the voltage across the device is zero. Similarly, whenever the diode or thyristor is off, there is a very negligible current. We ignore the current, so we say the current is zero. Okay, and there are some more assumptions. Suppose you give a gate signal in the case of a thyristor when it is forward biased. So it will go from off state to on state. Now there is a certain non-zero time taken to go from off state to on state. So we assume again here ideal device, we say that the time taken is zero. So it's all instantaneous. Now these are all simplifying assumptions. Okay. So we assume that the time taken to go from off state to on state is zero. And similarly, the time taken to go from off state to time taken to go from on state to off state is also zero. So essentially, we are neglecting losses also. So there is neglecting of the conduction loss. We are also neglecting switching loss. Now, please note, most of the analysis that we do are independent of these losses. Okay, so we are not doing any analysis which will require the losses, or which will require the time taken to go from on state to off state, or off state to on state, or which will require the voltage across the device when it is on. So such things are not required for the analysis. So these simplifying assumptions will help. Okay. So as I said, one can go from off state to on state by giving a control signal, but not the other way. So that's why thyristor is called semi-controlled device. That means the control is only in one direction, going from off state to on state, not the other way. So I gave some names directly. In fact, the examples were given directly for uncontrolled device, semi-controlled device, because we are aware of only one uncontrolled device, that is diode, and one semi-controlled device, that is thyristor. Now, when I am saying we are aware of only one example, I mean that these are the examples which are practical examples which can be used for power circuits at the transmission level. Okay. Now, when it comes to the third category, I'll come to the example, but this is the category of controllable devices. Now, there are examples there is more than one. More than one example is possible here. What are the examples? By now, you should be able to say what is this controllable. Yeah. First of all, controllable means I can go from on state to off state by giving a control signal. I can also go from off state to on state by giving a control signal. See, please note there are two circuits here: power circuit and the control circuit. So the power involved in the control circuit is very small. The amount of power, the amount of voltage, current, and power in the control circuit is very, very small compared to the voltage, current, and power in the power circuit. Okay. For example, in the case of thyristor, anode and cathode belong to the power circuit. Okay. The current that flows from gate to cathode is that of the control circuit. So the examples are, IGBT. I am talking about the ones which can be used in a high power circuit. There may be many examples, but the ones which are actually used in a power circuit. Before IGBT, there was one particular device, GTO thyristor, which stands for gate turn off thyristor. Of course, IGBT, insulated gate bipolar transistor. These two are very prominent. Nowadays, GTO thyristors are no longer required. In fact, IGBT is far superior. Now, the reason is the time taken from on state to off state, or off state to on state, is much smaller in the case of IGBT. So, it's always advantageous if you can go from on state to off state very quickly, off state to on state very quickly. So, IGBT can do that much faster than GTO thyristor. Now, since there are two examples, there can be a few more. Of course, there are commercially a few more available. I will not try to list all of them. what I will do in this case is I will use a very general symbol. So what I will do is I will just use a symbol like this, a switch with an arrow and two terminals. Let me call say terminal 1, terminal 2. Now there is an arrow on the switch, which means that whenever the device is on, the current is flowing, and the current is always flowing in one direction from 1 to 2. And when the device is off, there is no current flow. Now in this case I am not showing the control terminal, though there will be a control terminal. There is a control terminal in fact, but I am not showing that. Okay. Now we will first start with line commutated converter. Uh, Before going to the purpose of having such a name, or getting into the details of the operation of the converter, let me say a few things about thyristor. So a thyristor can be in one of the following states. Yeah, I already mentioned two states, on state, off state, but I will further classify this off state. So that actually gives me three states for the thyristor. One is forward biased, and blocking. The second state is forward biased and conducting. The third state is reverse biased and blocking. Yeah, by the way, I am using the word block. I mean, the thyristor blocks something. What does it block? Voltage. It blocks the voltage. Okay. So even though there is a voltage, it does not conduct. That's what is meant by blocking. Okay. Now, among these three states, which one is on state, which one is, so say I have not given a very precise definition of on and off, but I said that it is related to current flow. If there is a current flow, we say it's on state. If there is no current flow, we say it's off state. Okay. So only state 2 is on state. Okay. So 2 is on state. One and 3 are off states. So if I want to go from off state to on state, then can I go from 1 to 2 or 3 to 2? 1 to 2. So going from off state to on state is always from 1 to 2. So we say that transition from state 1 to state 2 is turn on. This transition is called turn on. Now if I want to go from on state to off state, so should I go from 2 to 1 or 2 to 3? It is invariably 2 to 3. The reason is, even if the current goes to 0, if I have a positive voltage of the cathode, of the anode with respect to cathode, the thyristor, continues to conduct. So there is a minimum time required for the voltage of the anode with respect to cathode to be negative. So there is a minimum duration for which the voltage is required to be negative, the voltage of the anode with respect to cathode. So only then it completely stops conducting. So this transition from 2 to 3 is called turn off. So what we saw in this class was I mean, the contents and a bit of historical developments and a very few assumptions that we make throughout the course. Okay.